So now we are in the position to answer the following question: is Cm star Rd equal to LRD? Meaning this the left hand side is the collection of Caratheodory measurable subsets, Caratheodory measurable sets with respect to the Lebesgue outer measure, M star, and on the right hand side we have the collection of Lebesgue measurable sets as we have defined them before. So the question arises whether if you use the Lebesgue outer measure M star and define the Caratheodory measurability condition and get a sigma algebra, this sigma algebra whether it is the same as the Lebesgue sigma algebra or not. And the answer to this question is yes. Answer is yes, and we will prove it shortly using some abstract nonsense if you want. So for this, let me make a quick definition. This is of a complete measure space. So if X, B, mu is a measure space such that every subset of mu null set is also measurable and hence null, then X, B, mu is called a complete measure space. Measure space. So this is to say that if E is an element of the sigma algebra B says that mu E is 0, so E is a null set, and if N is a subset of E, then this should imply that N belongs to B and mu N is also equal to 0. So this is the condition that should be satisfied for a measure space to be called a complete measure space. So of course an example we already know is the Lebesgue collection of Lebesgue measurable sets. This is with the of course the Lebesgue measure, so RD, LRD and M. The Lebesgue measure M is a complete measure space. Because when you have a Lebesgue outer measure 0, then a set becomes measurable. So the prototypical example of a measure space given by the Lebesgue outer measure on RD, Lebesgue measure on RD is a complete measure space. Now consider B, the sigma algebra B, as a Boolean algebra and mu as a pre-measure. So of course a Boolean algebra sigma algebra is a Boolean algebra, and a pre-measure, a measure is a pre-measure. So let me repeat, a sigma algebra is a Boolean algebra and a measure is a pre-measure. So you can consider B as a Boolean algebra and mu as a pre-measure on B. Okay. Then the Hahn Kolmogorov extension theorem, Hahn Kolmogorov extension theorem gives another sigma algebra, a sigma algebra B prime containing B, and a measure mu prime on B prime such that mu prime restricted to B equals mu. So we are using the Hahn Kolmogorov extension theorem for the specific case when you already have a measure and a sigma algebra B. Then we can generate another sigma algebra B prime and a measure mu prime such that mu prime equals mu. Now note that anything that you get from the Caratheodory extension theorem is going to be a complete measure space. So I will put this as a lemma to check for you. So a measure space obtained via the Caratheodory measurability condition or the Caratheodory extension theorem is a complete measure space. So this you can check. Now the question arises whether B prime is equal to B or not, and this is answered in the following lemma. So this is left as an exercise for you, and this lemma says that if X is sigma finite, meaning that X is a union of countably many subsets Xj, Xj is subset of X for each j, such that mu of Xj is finite for each j, then you can say that B prime equal to B. So when you already have a complete measure space on a sigma finite space, then you have B prime is going to be equal to B. So here we are assuming, so provided that X B mu is a complete measure space. So let's see why this lemma will imply that. I claim that this lemma implies that Cm star Rd equals LRD, because when you take the start with the measure space Rd, LRD, so this is our X, this is our B, and this is our mu. This is a complete measure space, and then we note that and Rd is sigma finite, since Rd can be written as the union of Euclidean balls with center 0 and radius n, and of course the Lebesgue measure of these balls B0n is finite. So Rd is sigma finite with respect to the Lebesgue measure, and so both these conditions for our lemma are satisfied, which is that X be sigma finite and that it should be a complete measure space. So this implies that this B prime, so B prime is nothing but this CMRD, this is B prime and this is B. So the lemma says exactly that B prime is equal to B. So we would have shown that once we show the lemma, we would have shown that the Caratheodory collection of Caratheodory measurable sets is equal to the collection of Lebesgue measurable sets. So I leave it to you as an exercise to check the details of this implication, that the lemma implies this. Check the details. In particular, show that we have that the infimum of, so for any set E in Rd, the infimum of the elementary measures of boxes such that E is covered by the union of the boxes is equal to, so this is nothing but of course the Lebesgue outer measure E, but this is also equal to the infimum of the sums when you replace boxes by measurable sets rather than so you replace boxes by measurable sets in general. So here BI are boxes, and here EI belong to the Lebesgue sigma algebra for each I. So one has to show this equality to conclude that because the left hand side is the Lebesgue outer measure and the right hand side is the outer measure. So here I should rather write, no, it's okay. So this is the Hahn Kolmogorov prescription when you go from pre-measure to an outer measure and then use the Caratheodory measurability. So we have to show that the two outer measures given by these two formulas are exactly the same. So once you show this, then the lemma implies that the collection of Caratheodory measurable subsets of Rd with respect to the Lebesgue outer measure is the same as the collection of Lebesgue measurable subsets of Rd. So now let's see the proof of this lemma. So we have to show that if E belongs to B prime, then E belongs to B. So remember that B prime, so remember that we had X V mu, a complete measure space which gave via the Hahn Kolmogorov extension, Hahn Kolmogorov extension theorem, another sigma algebra B prime and mu prime on B prime, such that mu prime when restricted to B prime, when restricted to B, is exactly mu, and so we can write B prime here as C mu of, well, not mu but mu star, which is generated the outer measure induced by the pre-measure mu. So this mu star is defined via mu. It's a pre-measure defined via mu. This is the Hahn Kolmogorov procedure to go from Boolean algebra and a pre-measure to a complete measure space. Now we are already starting with the complete measure space, and we have to show that whenever we have X is sigma finite, then B prime is a subcollection of B, and so B prime is equal to B. So how do we show this? So if suppose first that the measure of E is finite. So then I claim that there exists a set A in B such that E is a subset of A and mu prime of E is equal to mu of E. So this is for any set E in the bigger sigma algebra B prime. So let's see how to prove this. So to prove this claim, we proceed as follows. So for each n greater than or equal to 1, let AI be a collection of elements in B covering E. So AIN I equal to 1 to infinity, such that this sum mu AIN I equal to 1 to infinity is less than or equal to mu prime E plus 1 over n. So set A n to be the union of AINs, which means that E is a subset of AN and mu AN. So this belongs to B, so we can write mu AN is bounded above by this sum mu AIN, and then this is bounded above by mu prime E plus 1 over n. So now if we define A to be the intersection of all these ANs, n equal to 1 to infinity, then E is a subset of A, so mu prime E is less than or equal to mu prime A, which is equal to mu A, because again this A belongs to B because it's a sigma algebra. So we have mu prime E less than or equal to mu A. On the other hand, mu A is less than or equal to mu AN for any n, and so this is less than or equal to mu prime E plus 1 over n for any n greater than or equal to 1. This means that mu A is less than or equal to mu prime E, and this means that mu prime E is equal to mu A. So we have shown that for any set E in B prime, so E was in B prime and there exists a set A in B such that mu prime E equals mu A. So now if you take the measure mu prime of E minus A, this is equal to mu prime E minus mu A, right? Because, well, it's equal to mu prime E minus mu prime A, and this is equal to mu prime E minus mu A, and this is equal to 0, as we have shown. Here I am using that mu prime itself is also a measure, so we have this. So now using again the fact that this belongs to B prime, and so this implies that there exists a set n in B such that mu prime E minus A is equal to mu n is equal to 0, and E minus A is a subset of this set n. From what we have just shown, here again we have a set of finite measure in B prime, so we can find a set n in the sigma algebra B for which the measures agree, and in this case it is 0. So this means that E minus A is a subnull set, which means that E minus A is mu measurable. This is E minus A belongs to B because X B mu is a complete measure space. So E minus A belongs to B. So here actually I should rather take A minus E rather than E minus A, because E is a subset of A. So we have A minus E everywhere rather than E minus A. So now E also here, A minus E. So E can be written as A minus E, and so this belongs to B. Now so this proves the statement when E has finite measure. So if mu E is infinite, then E can be written as a countable union, n equal to 1 to infinity, of the intersection with xn, where x is the union of xn, n equal to 1 to infinity, with mu xn finite for all n. So now we can say that even if E has infinite measure, then each of these is finite measure. Mu of E intersection xn is finite, and so therefore each of these sets belongs to B, and so the union belongs to B, and then we are done. So we showed that any completion that you get for a complete measure space via the Caratheodory extension theorem gives you nothing extra, and you get the same sigma algebra back when X is sigma finite.